I wanted to start today by kind of finishing out and doing some more examples with balancing chemical equations and kind of applying some of those things that we saw in Wednesday's class. And then I asked you to very quickly turn around and use in your PLTL and in the assignment that was due last night. So let's do a couple more practice problems, and that way, if this is something that just hasn't clicked in yet, hopefully we'll get to a point where it's clicking a lot better by the end of today, or certainly by the end of next week. So we're asked to balance this equation. So setting up our organization here, I've got iron, oxygen, and hydrogen in this reaction. And looking at my subscripts, I've got 3 irons, I've got 4 oxygens, and I've got 2 hydrogens here on the reactant side. On the product side, I have 1 iron, 1 oxygen, and 2 hydrogens here. So right away, I look at this and say, okay, with the exception of the hydrogen, nothing's balanced. And the only thing that I know based on the hydrogen is right now it currently is balanced. And since hydrogen is only present in 1 molecule on each side, logically speaking, I can kind of infer that whatever the coefficients are for 1, they're going to have to be the same on the other side because the 2 are already balanced out. But one thing I can definitely point to here, one of the tips that we had in our tips for balancing is anytime we see these multiple subscript compounds, that is a good sign to tell us what the coefficients might be on the other side. Because to get 3 irons, I'm going to need 3 iron atoms here. And to get 4 oxygens, I'm going to need 4 water molecules. Now, changing the number of water molecules does change my amount of hydrogen as well. I had 2, now I have 4 times 2 for 8. But this is what I was saying, because I know that the hydrogen is the same in each compound, as soon as I had that 4 on the water, I knew that I was going to have to put a 4 on the hydrogen to balance it out, because that's the only place where hydrogen existed. 4 times 2 gives me 8 hydrogens there. Now I've got a balanced chemical equation. So when it comes to these kinds of problems, that's the kind of stuff that we want to be on the lookout for. Is, can I find one of those little places where there's a little hint or a little trick that's going to help to at least get me started on the balancing so that I can figure out the rest as I go. Multi-subscript compounds are a really good place to start for that kind of information. All right, let's look at another one. All right, this one is in pair deck. We're going to do it together, but I want you to get the participation credit points while we do it. So if you are in pair deck, you want to look for slide number 4. And so we're going to set this up. I've got methane reacting with oxygen to make carbon dioxide and water. Based off of the kind of the skeleton of this, immediately your brain should be going combustion, because I've got oxygen reacting, I've got carbon dioxide and water as products. Those are kind of the hallmarks of combustion. Now for this combustion reaction, we've got carbon, hydrogen, and oxygen involved. On the reactant side, I have 1 carbon, 4 hydrogen, and 2 oxygen. On the product side, I have 1 carbon, 2 hydrogen, and I've got 2 oxygens in carbon dioxide, plus 1 oxygen in water for a total of 3. Now, here's something to point out and just be generally aware of when it comes to combustion reactions. Combustion reactions almost always have this multi-subscript thing that we can work off of. Now, it doesn't look like that for methane until you realize that I have 1 carbon here and 1 carbon here, so it's already balanced. I didn't have to do anything anyway. But for the hydrogen, I bring the hydrogen, look over to the water, and see that for the 4 hydrogens that I need, I only have 2 per water, so I need 2 waters to give me those 4 hydrogens. 2 times 2 gives me 4 hydrogens. 2 times 1 now gives me 2 oxygens, plus the 2 that are already here, for a total of 4. So I've got my carbons balanced, my hydrogens balanced. The only thing that isn't balanced is oxygen. Now, we had a similar problem to this on Wednesday and got into trouble because we had an odd number of oxygens on one side and an even number on the other side. And we ended up having to set up a fraction and multiply by 2. This isn't the case here, though. I have 4 oxygens over here and 2 here. 2 times 2 will give me the 4 that I need. This is balanced right now. And what this leads me to is a really important rule of thumb when it comes to combustion reactions. When we're looking at combustion reactions and we're trying to balance them, the number of carbons ultimately tells me if I'm going to have to double everything or if I can balance it straight up. And the rule of thumb is this: if I have an odd number of carbons, I will be able to balance it straight up. If I have an even number of carbons, I'm going to end up having to double it. Now, we already can see the odd example here. Let's just go backwards in time just a little bit to Wednesday. This one that we had to do the extra work on, it was an even number of carbons. 8 carbons, I had to double it. 8's an even number. So the number of carbons is even. Better chance I'm going to have to end up doubling everything along the way. And so the trick rule of thumb that you see is if I have an even number here, I start with 2 of that molecule and I balance everything else from there. If I have an odd number like I did here, I can balance it straight up without starting with the double. All right, let's look at one more here. So this would be slide 5 in the pair deck. Now, in Wednesday's class, I made mention of the idea that if you have a cluster of atoms together, that you can treat them as a single unit rather than as individuals. Problem was, we never got a chance to use it on Wednesday. And so when you saw it in your PLTLs, I know this was a source of confusion for a lot of you, based on the reports I was getting back from the leaders and from some of you personally. What we need to recognize, what we can recognize, is that On both sides of the equation here, I have SO4s. Why that's important is because since I recognize that there is a consistency, an SO4 on each side, rather than split it up into sulfur and oxygen, I can keep it together as SO4, which makes the balancing a lot easier because now I only have to track aluminum, hydrogen, and sulfate, SO4, instead of aluminum, sulfur, oxygen, and hydrogen. It sounds like a minor difference. After all, what's one more thing? But it makes a world of difference when you look at something like aluminum sulfate here. And instead of having to distribute this 3 and come up with 3 sulfurs and 12 oxygens, I can instead just go, oh, there are 3 sulfates here. 3. And there's 1 sulfate over here. 1. And for the rest of them, I just follow the subscripts. 1 aluminum, 2 hydrogens on the reactant side, 2 aluminum, 2 hydrogens on the product side. By keeping those clusters together, it makes the balancing a lot easier because there are fewer things to keep track of. There's less places to make mistakes. Now, in addition to having the clusters, I also have a multi-subscripted compound here in the aluminum sulfate. I can use those multiple subscripts to drive the balancing because I need 2 aluminums, so I'm going to need 2 aluminums on the left side. And I'm going to need 3 sulfates, so I need 3 sulfuric acids to do that. Now, in that process, my hydrogens went from 2 to now it's 3 times 2. 3 times 2 is 6. So everything is now balanced other than the hydrogen. But hydrogen's by itself over here. To get 6, I multiply this by 3. 3 times 2 gives me the same 6. Now it's balanced. So in pair deck, you would enter this as 2, 3, 1, 3. Because all you're doing is just adding the coefficients in as the code. For the previous problem, I think it was 1, 2, 1, 2. Yeah, 1, 2, 1, 2 was the code for the previous one. Okay, so that is what we're trying to do with balancing. And like I said on Wednesday, this is a skill that is acquired over time. It's not something that you're going to get instantaneously. So organizational methods like this can help you to at least keep track of things as you build up skill. And so hopefully between the PLTL and the practice exercises and the end of chapter assessment, the chapter 7 review, hopefully you're going to get enough of this, and we're going to keep working on this because equation balancing is kind of the bedrock keystone feature for what we're going to do in chapter 8 when we actually use those balanced chemical equations to do calculations. So this is something that we're going to keep doing, we're going to keep building on. So again, if it's not immediately coming to you, that's okay. We're working on it. Hopefully sometime between now and November 3rd, it'll click in for you and make sense. But it's something you're going to have to work on too. So take advantage of these extra activities. And if you need more practice, I've got lots of ways to help you practice. So the main topic for today is solubility. What we are trying to do is we are trying to define solubility and trying to use some basic guidelines to help us predict when a reaction takes place versus when it does not take place. So some vocabulary for us. The term soluble means that it will dissolve in whatever liquid it is that we're trying to dissolve. Now, for our purposes, since we are most often talking about aqueous solutions, when we use the word soluble, we're going to be talking about solubility in water. So if I describe something as soluble, I mean that it dissolves in water. If I describe something as insoluble, that means that it does not dissolve in water. So those are the two main terms. Soluble if it does dissolve in water, insoluble if it does not dissolve in water. And just as a reminder, again, we're talking mostly about water here. So aqueous solutions are solutions where water is the solvent, which in our case is basically all of the solutions that we're going to be describing, all the kinds of solutions that you're going to deal with in lab. So soluble means it dissolves, insoluble means it does not dissolve. For our purposes, the biggest application of solubility is in precipitation reactions. Now, we referenced precipitation reactions last Friday. The idea that if I take two solutions and I put them together and a solid forms as a result of the mixing of those two solutions, that is a precipitation reaction. The solid that forms is something called a precipitate. The reaction that we are referencing here, at least in this case, we are looking at the reaction between potassium iodide and lead 2 nitrate. Potassium iodide is in this burette here. And we can see from the burette and from the stream coming out of it that potassium iodide is a solution. It is clear, it is colorless, there is no solid in it. The potassium iodide has been fully dissolved in that water to make this solution. And if we look at the potassium nitrate, at least in the part that has not come into contact with the potassium iodide yet, we see the same thing. The lead 2 nitrate is clear, it is colorless, there is no solid in. Lead 2 nitrate is soluble in water. And yet, when they combine, we get this yellow solid forming as a result. Now, the yellow solid is a compound known as lead 2 iodide. But the question really becomes, how do we know that it is lead 2 iodide that is the solid here as opposed to the potassium nitrate? Because if we follow this, we see that this is a double replacement reaction, double displacement. Potassium and the lead switch places. And so how do I know that it's the lead compound that gives me the yellow solid and not the potassium compound? Well, to understand that question and to understand the answer to that question, we have to understand a key principle about solubility. when it comes to precipitation reactions, only the insoluble compounds are going to make precipitates. So in order for a precipitation reaction to take place, I need to get a product that does not dissolve in water. Now the question becomes a matter of, how do I know whether it dissolves or doesn't dissolve? To answer that question, we have to rely on something known as the solubility rules. Now, solubility rules are, I really caution on calling them rules because rules imply absolute. These are more like guidelines in the most case. And what these guidelines tell us is they tell us a pretty accurate way of determining and predicting whether a substance is going to be soluble in water or insoluble in water. And therefore, if we identify it as a product in a reaction, we can identify whether it's going to dissolve in water and therefore stay dissolved, or if it's actually insoluble in water, we'll see it as a precipitate. Now, within these solubility guidelines, there are three main categories. The first category is this one. These are the ions that are always soluble in water. Now, before the look of dread on your face fully encapsulates your brain, let me give you a little bit of sunshine here. I am not requiring you to memorize the solubility rules. That's a Chem 105 thing. Chem 105, you have to be able to know these by heart. These will be given to you in the form of a paper reference for your own ability. I'll also put this in Blackboard so that you can use it to help you with the homework this weekend. So don't get crazy on trying to remember all this stuff. I will give you some pointers that help you remember things so that for those of you that do move on to Chem 105 and you have to memorize these solubility rules, you kind of already have a little bit of information at your disposal to help. But you do not need to memorize them for today. You do not need to memorize them for the third exam or for the final or anything like that. This first group, though, this is the only absolute group. So when we say always, that's always with 200 lines underneath it. There are no exceptions to this group. Not only are the salts of this particular list always soluble in water, they're usually really soluble in water. And the ions that we would look for are these: nitrates, acetates, chlorates, the ammonium ion, and anything out of the alkali metals, group 1. So if we encounter a potassium compound, automatically we know it will dissolve in water because all potassium compounds dissolve in water. If we encounter an acetate, lead-2 acetate, manganese acetate, mercury-4 acetate, whatever. I just named a bunch of compounds that don't exist. Ignore that. But even if we have this, the fact that they are attached to an acetate, we know that they'll dissolve in water. That's the point. So in this list, these are the absolutes. These are the ones that will always dissolve in water. They're always soluble. Like I said, put a couple underlines around that always, because this is the only rule that has that level of absolute to it. The other two rules that I'm going to present, the other two groups, have some asterisks on them, have some exceptions associated with them. For our second group are ions that we would see that usually dissolve in water, but there are some exceptions to them. In this group are the halide ions, so the ions of halogens, chlorine, bromine, iodine, the chlorides, the bromides, and the iodides. In this, there are 3 known exceptions. The known exceptions are mercury 1, lead, and silver. Now, I'm going to throw you back into my own personal Wayback Machine. We're going to go back to the year 1999, and a young Professor Bruck, who is in his first chemistry class ever, is learning the solubility rules from his chemistry teacher. And my chemistry teacher gives me this little way to remember the exception. Merle's halides are the ones that are insoluble. Now, who is Merle and why does he care about halides? I don't know. But Merle's standing in for mercury, lead, and silver. Those 3 are the exceptions to the chloride. So I know that the chlorides are usually soluble, but Merle's chlorides are the ones that are not. And so if I encounter any of Merle's chlorides, I know that it's going to be the one that does end up precipitating, one that does not dissolve in water. Now for the sulfates, we have the same kind of thing. There is one exception here that was not listed. For the sulfates, again, sulfates are usually soluble. The ones that aren't are Balckamer sulfates. Now, the Balckamer sulfates, barium, lead, calcium, mercury, strontium. One thing that could get you in trouble, because I've seen it happen, is the S's in these 2 exception devices are different. I have seen students, and I don't mind it at all, put an SR here at the end of Balckamer's so that they remember that it's strontium, not silver. Because with these 2 names, it can be easy to confuse the 2. But again, this group, if you see a sulfate, most sulfates dissolve in water. If you see a bromide or an iodide or a chloride, most of them dissolve in water. There are a couple of exceptions to those. Those are the exceptions that are listed out here. So we have presented the always solubles, the usually solubles. The only group left would be the ones that we haven't talked about, which are, well, what doesn't dissolve? And so the third group is the usually insolubles. Now, one thing before I reveal that group of usually insolubles. The list I'm about to show you is a non-exhaustive list. Basically, I've given you the most common examples. If you encounter other kinds of examples, you can generally put them into the same category as this third list. And the third list, most of the exceptions on that third list aren't really exceptions at all. Because the majority of the insolubles that do dissolve because they're attached to something from that first list. So on this list are sulfides and hydroxides. I've outlined them separately, mainly because in addition to ammonium ion and alkali metal ions, which were on the first list anyway, and remember that first list, we put 200 lines under always because we really meant always. The reason these two get sucked out separately is they also dissolve with alkaline earth metals. So barium sulfide, that one will dissolve in water. Calcium sulfide, that one will dissolve in water. Calcium hydroxide, that one will dissolve in water. Magnesium hydroxide, that one will dissolve in water. And so from that perspective, those ones are a little bit different because everything else on this list, including the ones that aren't on this list that you might encounter, are always insoluble unless they're paired up with ammonium ion or an alkali metal ion. So carbonates are usually soluble, but if I have ammonium carbonate, ammonium's always soluble, so ammonium carbonate's going to be soluble too. Phosphates are usually insoluble in water. If I throw it in with an alkali metal, lithium phosphate is going to dissolve in water because all lithium compounds dissolve in water. So this third list has exceptions, but the exceptions are all tied back to that first rule. And the only ones that aren't are the sulfides and the hydroxides because they also are soluble with the alkaline earth metals. So those are the solubility rules or solubility guidelines, however you want to frame it. The question becomes, well, how do we use this information? What exactly do we do with what we have been given? And to answer that question, I want to come back to the lead-2 iodide pictures that we started with. So if I were to look at each of those solutions from a molecular standpoint, what I would notice is that since the potassium iodide is soluble in water, when ionic compounds dissolve in water, they break apart into their individual ions. So I end up having iodide ions and potassium ions, and they're all just kind of floating around in this water. And the same is true for the lead-2 nitrate. I've got lead ions and I've got nitrate ions, and they're all just floating around in the water. Based on the solubility rules, even if I did not have these solutions at my disposal, if I had the solids, I would still predict that they would dissolve in water because potassium compounds always dissolve in water, and nitrate compounds always dissolve in water. They're both on that first list. So I would predict that these two solutions would dissolve in water, even if I didn't have the solutions, even if I had to make it myself. When I put them together, now all four of those ions are present at the same time in this solution. Now, we recognize this as a double displacement reaction, which means that the potassium ion and the lead ion have to switch places. So my possible combinations of ions include what I already have, plus lead-2 iodide for the combination of lead and iodide, and potassium nitrate for this one. Using the solubility rules, I could look at this and say, okay, well, potassium compounds and nitrate compounds always dissolve in water. This is going to be soluble. Since it's soluble, we would write it as AQ or aqueous for its phase. For the lead-2 iodide, solubility rule on iodide is that it's usually soluble. The only iodides that are insoluble are Burroughs iodides, mercury, lead, or silver. And lead happens to be one of those exceptions. As an exception, instead of it being soluble, we would expect it to be insoluble. As an insoluble compound, it's not going to be aqueous because it's not going to be dissolved. It's going to show up as a solid. It's going to be my precipitate. So without actually mixing the two substances together, I can predict what's going to happen here. My prediction is that I'm going to get a solid. That solid is going to be lead to iodide. And when I actually mix them together, that's exactly what happens. The potassium and the nitrate stay ionized because they're still in solution. The lead to iodide solidifies and drops to the bottom because it's more dense than the water. And we end up getting that solid as a result. So the thing that we do with our solubility rules is we can use those solubility rules to predict the results of a reaction. Now let's look at a different kind of reaction. This time, we have the reaction between potassium iodide and sodium chloride. And you can see when we mix those two together, they started as clear and colorless liquids. I mixed them together, it's still a clear and colorless liquid. If I do my double displacement, and I switch places, I end up getting KCl, potassium chloride, and sodium iodide. Now, based on the solubility rules, right away, I would look at this and say, well, hold on, potassium chloride, potassium compounds are always soluble. So this is soluble, which means that this is aqueous. Sodium compounds are also always soluble. Soluble, so this is aqueous. Do I see a solid product based upon my solubility rules? No. So when this happens, we classify this as this is a no reaction. Our eyes tell us that it's a no reaction. And the chemical equation and the solubility rules also predict that a reaction would not occur here. So when that happens, when our solubility rules predict that there is going to be no net change, we say that that's no reaction. So one of the troubles of double replacement or double displacement reactions is that it is presumed that because the ions switch places, that a chemical reaction is actually taking place. What the solubility rules help us to show is that if we don't get a visible reaction, the solubility rules help us to prove why no reaction was there. Because we can look at the product and say, oh, those products were not soluble, or those products were soluble, and since there were no insoluble products, there was no reaction to be had. So what you're going to be asked to do in this assignment over the weekend is a couple of things. First of all, just a general, do you understand the solubility rules? If I give you a compound, can you tell me if it's soluble or insoluble? But also doing stuff like this. If I give you two substances and I tell you that's going to react, can you predict the products and determine if that is actually going to give us a precipitate or if it's going to give us nothing? How do you know? Well, by being double replacement, you switch the ions. And then you use your solubility rules to predict solubility of the products. If both products are soluble, then you know that no reaction took place. If both products are insoluble, that does happen sometimes, then you just make note that both products will form solids. But usually what is the case is we end up getting one solid and one not solid, one that stays in solution. Let's take a look at one example problem, and then we'll put it away for the week. So here we have calcium chloride reacting with magnesium sulfate. Now, double displacement tells us that the calcium and the magnesium are going to switch places. So I'm going to end up with magnesium and chloride. We want to make sure we get our formulas correct, so we look at the charges. Magnesium's +2, chloride's -1. The charges don't match, so we cross 2 chlorides to give us the correct formula. The other product would be calcium with sulfate. Periodic table says that calcium is a +2 ion. Sulfate, we just need to know it's a -2 ion. Since the charges match, we don't need to do anything further. Calcium sulfate is CaSO4. So that's the first step always. First step always is if I'm doing double displacement, I switch the ions. I write the formulas for the two products. Now we evaluate solubility. Okay, for magnesium chloride, the rule is that chlorides are usually soluble. The only exceptions are the Merles chlorides, mercury, lead, silver. Magnesium is not one of those exceptions. It's not mercury, it's not lead, it's not silver. This is soluble. Since it's soluble, it's going to be aqueous. For the calcium sulfate, sulfates are usually soluble. The exceptions are the Balcomers sulfates, barium, lead, calcium, mercury, strontium. Calcium is one of those exceptions. So since sulfates are usually soluble, the exception would be that it is insoluble. So we would mark that with a solid. So do we predict a chemical reaction take place here? Yes. We're going to see the solid calcium sulfate form. That is going to be our precipitate. All that's left to do, since we have a chemical reaction, is to make sure that it's balanced. This is a prime example of one that you can do by inspection. Just because you can look through it, since there aren't a whole lot of subscripts here. I see I have 1 calcium and 1 calcium. I've got 2 chlorines and 2 chlorines. I've got 1 magnesium and 1 magnesium. I've got 1 sulfate and 1 sulfate. I need to do nothing further. It's already balanced as is. So on Monday, we will do a little bit more of this. We'll do a couple more examples just to kind of review. In your pair deck, go to slide 8 and answer that last question before you leave. And once you do, have a great weekend. I'll see you on Monday.